Hello dear students, I hope you are fine and safe with your family. Today we are going to start formally the lecture regarding second order partial differential equations. Let's just remind what we have already completed regarding the course of partial differential equation. We have completed linear first order partial differential equations, quasi-linear and non-linear first order partial differential equations, and we have also studied one famous method for solving these type of problems, and this is called method of characteristics. So regarding partial differential equations, we have completed these three topics. So today we are formally going to start what are second order partial differential equations and which part we will going to focus in this lecture series. So I am going to start formally with the definition that what do you mean by second order partial differential equation. It is just written in the simplest form as any general equation of any general relation between the partial derivatives of first order and second order. What I mean to say that, if you remember that we have written x, y, z, which was function of x, y, and p, q. You know that p is equal to partial z by partial x and q is equal to partial z by partial y. This was called generally the equation of first order partial differential equation. Okay, I am writing this is first order, generally first order partial differential equation. Okay, it's not necessary this is quasi-linear, semi-linear or any non-linear or rather linear partial differential equation. This is the most general form to write any first order partial differential equation. So there will be some general form writing second order partial differential equation. So this is written as like that: x, y, z, which also depends upon x, y. So remember that we are writing the examples or definitions of partial differential equation of second order in two independent variables. Okay, we are not going to start the study with respect to three independent variables. So there are only two independent variables and their partial derivatives: zx, firstly zx, okay, zy, okay, z. Now there will be some second order derivatives as well. So there will be zxx and zxyy, okay, zyy and zxy, because there will be some mixed derivative as well. So generally this is the form of second order partial differential equation, which means any relation between the independent variables, dependent variable and their first and second order partial derivatives at most equal to 0. This is in general is regarded as second order partial differential equation. Okay, second order partial differential equation. So this is our topic and we are going to start this with a particular case for a relation. Name that relation as 1. Okay, so equation 1 is generally second order partial differential equation, but we are going to start particularly. So particularly we shall focus on linear second order, okay, linear second order partial differential equation. So this I have written in the lecture slides, that consider the following general second order partial differential equation in two independent variables. So this is the most general form of second order partial differential equation, but remember that this is linear. Generally, I have already told you earlier that any relation between zx, zy and their second order derivatives equal to 0 will be regarded as second order partial differential equation. But to handle general form of second order series is not so easy. Even to solve general form for linear second order partial differential equations is also not so much easy. You will study in the later lectures that we will focus and converge towards canonical forms in order to solve easily the second order partial differential equations which are linear as well. So what I am trying to explain you that to study and solve any non second order partial differential equation is not so much easy. So we are focusing our attention towards linear second order partial differential equations, and we shall adopt some methods to solve linear second order partial differential equations, which include for example canonical forms and later on some integral transforms and method of separation of variable as well. But in your lecture, in your course, there are some methods included, so we shall focus on one or two basic methods in order to solve linear second order partial differential equations. Okay, so let's formally start the lecture with second order linear partial differential equation. So generally we are given in the linear case, this is analogous, okay, this is analogous to second order homogeneous, okay, polynomial in x and y. So in general any relation of x y polynomials actually give you the idea how to write second order partial differential equation. So what is the general form of second order polynomial? This is the general form, okay, you all know from basic algebra, plus ex plus fy plus some other constant g equal to 0, and the particular cases for the graph of y in terms of x for that relation, you all know that was conic section, parabola and hyperbola as well, and ellipse. Now we will try to focus on first order linear second order linear partial differential equation by using this analogous idea that what is the general form. So general form is capital A partial square, okay, partial square z over partial x square, okay, partial x square. A is a coefficient. I will tell you later what can be A and B and other constants. So partial z over partial y square, but this is given with constant c generally because the mixed term is written firstly. So you will write partial x over partial y, okay. This is the second term, plus d, okay, plus d partial partial z over partial x, okay. This is the now linear term, plus e partial z over partial y, okay. Now there will be some extra term because there will be one term with no derivatives. This will be general any function z, but this is also given with respect to some constants capital F z plus g equal to 0. This is our required equation which will be studied now, and that equation is called linear second order, okay, second order partial differential equation. Now what are A, B, C? So I am writing for you. A depends upon x, y generally. B also depends, sorry, there is B, I'm sorry, I forgot. B also depends upon x, y. C also function of x, y. Similarly all other constants. Okay, let's formally write the constants. Okay, so what can be A, B, C, D, E, F, G? You can see on the lecture slide that A, B, C, D, E, F, G are functions of the independent variable x, y, which we have written, and the equation 1 can be, and they are continuous with partial derivatives. So I was telling to you that A, B, C, D, E, F, G are continuous and their partial derivatives also exist and they are also continuous. Okay, but which partial derivative which is necessary for your calculations? Okay, so basically which is used in the literature or in the theory, A, B, C, D, E, F, G are continuous and have first and second order derivatives are also continuous. What I am saying to you that for any, okay, for A, so A is continuous, A is continuous and partial, okay, okay, we can write easily like that. Partial A over partial x exist and also continuous. Okay, similarly partial A over partial y exist and also continuous. The important point is that at which point or at which domain partial A over partial x and partial A over partial y will exist and will be continuous. They will be continuous at the prescribed domain of A. Okay, A has domain x, y. The domain can be any subset of R square. So on that particular domain, A will be continuous, partial A over partial x will be exist and continuous. Similar will be partial z over partial A over partial y. But not only for first order derivative, you have to do that for second order derivative as well. So generally for A we have partial square A over partial x square also exist and it must be continuous. Okay, okay. So this is going to happen only for, not only for A, this will happen for all coefficients A, B, C, D, E, F, G. I have given you one example regarding A. So this will happen actually for B, C, D, E, F and G. But if you look at in the slides, we have taken only ABC because I will later explain you why we only actually need ABC in order to study and solve the second order linear partial differential equation. So generally A, B, C, D will be functions of x, y, and now remember that they will be continuous, their partial derivatives with respect to x and y will exist and also continuous, not only first order, the second order as well. Okay, let's move on towards some general theory that how you will study linear second order partial differential equations. Remember that you have domain or specified domain at which A, B, C, D, E, F, G depends. Just transform your problem into some new form like that. You have a, b, c, but all other linear terms, I mean to say linear and zeroth order derivative term, and merge that all part in f of x, y, ux, uy, u, any relation between, because this is first order. What is this actually? D partially over partial x plus e partially over partial y plus f u plus g equal to 0 plus g something equal to 0. Actually this is the linear first order partial differential equation part. So we have actually separated linear and zeroth order terms and second order terms. So this part is very important for us in order to develop some theory regarding this linear second order partial differential equation. And you know, formally I have written that partial over partial x is ux and uy and so on. This is the notation which we always use. So actually what we are going to describe in that lecture, the classification for partial differential equations, but only for second order and they are linear. So actually there is more subsection for a linear second order partial differential equation. So I have named that as classification, and this classification was motivated by the second order polynomial. Remember that this curve, this is a second order polynomial equation 3, and if you remember that from classical basic algebra, the behavior of obtained curves y in terms of x, if you draw the graph depends upon only 3 coefficients a, b, c, and from the classical conic section you must understand that the behavior of the curves depends upon the discriminant, which was b square minus 4ac. If it is positive, then the curve traces out hyperbola. If this is equal to 0, then the curve traces out parabola, and similarly if less than 0, the curves trace out to be ellipse. Okay, depending upon the sign of the discriminant b square minus 4ac. This was in the basic classes, but motivated from that idea, the partial differential equations which are analogously written by the well known second order polynomial equation in x and y, the classification depends upon again only to the initial part, which we have written as auxx plus buxy plus cuyy, and the other part is written as f of something. Okay, so this part which has second order derivatives is called principal part, and the part which have for any linear second order partial differential equation, the part which have only first order derivatives and zeroth order derivative, I mean to say the function itself, this part is called non-principal part. Okay, and now okay, we have named that principal part for polynomial equation, but it is also for partial differential equation. These are the examples which we can study. Okay, so the nature of equation 4, or I mean to say the properties or classification of equation 4 depends upon the coefficients or this operator. Okay, I have written this as an operator, and sorry, and yeah, you can classify this equation as hyperbolic, parabolic, or elliptic, similar to the polynomial equation. So for classification we attach a symbol to 5 as p of x y equal to this. This is a discriminant, this is a polynomial in x and y, and we are trying to develop the idea similar to what we have developed earlier regarding discriminant. Okay, so something like that, as we have replaced x by partial over partial x and y by partial over partial y, something like that. So depending upon the sign of the discriminant b square minus 4ac, similar will happen, that equation will be hyperbolic, parabolic, or elliptic respectively. So linear partial differential equation with variable coefficients. The above classification is valid if the coefficient e are dependent upon x, y. remember that we have taken a, b, c, d as constants, okay, a, b, c, d, e, f, g as constants earlier, but the main idea is that this classification also valid for any a, b, c, d, e, f, g which depends upon x and y. So in that case, what will be the discriminant? Discriminant will look like that. Okay, so there is a time when we should focus more carefully. B square minus 4 a c. Okay, if this is equal to 0, the equation will be parabolic, and greater than 0 hyperbolic, and less than 0 similarly elliptic. But there is one question. For example, we take the case 1. Okay, case 1. So in that case, this is positive, okay, strictly positive. A question arises that at which domain this quantity, so okay, name that as delta, okay, we are naming this as delta function of xy, or any polynomial you can also name p of xy. I think named that as p of xy. No problem, you can name p of xy or delta of xy. Classically in the books we have written delta, so you can name delta as well. So this delta sign not only depends upon BAC but also depends upon x and y. Sometimes you will be given the question that in which domain is your partial differential equation is hyperbolic, because we are taking hyperbolic case just for understanding. Similar cases can be discussed on the same pattern. Okay, in which domain your partial differential equation is hyperbolic. For that you must know at which points this quantity is strictly positive. So if this quantity is strictly positive, for example, for x equal to 0 and y negative, so you say that your quantity your equation is hyperbolic in the region. So you have to mention the region. What is the region? You will simply write in set builder notation x comma y which belongs to R square. This is very easy to write in set builder notation, which belongs to R square, such that x is 0 and y is negative. So in that region your PD or partial differential equation will be hyperbolic. This is an example, and I am not saying that this is going to happen always. I am telling you the exemplary case that how you should focus and you proceed when you have a, b, c, d in general variables and depends upon x and y. So if they depend upon x and y, you must calculate the discriminant. Okay, after the calculation you have to focus and analyze at which points x and y your quantity delta will be strictly positive. If for example, this is an example, okay, this is an example. If for example x equal to 0 and for y negative, that delta, okay, that delta is positive, okay, so you will say this is positive for which, for you have to say that for all x y belongs to the region this, which belongs to the region this. Region, what is the region? X is 0 and y is negative. You have that quantity as well, because you have to mention the region in as a subset of R square. So this is one of the question which arise usually when studying linear second order partial differential equations. So there are some examples as well. So if you say that an equation is hyperbolic, hyperbolic at a point xy. You say that equation is parabolic at a point, and similarly elliptic at a point or some region as well. Maybe you are having a case where x will be 0 and y will also be 0. So then we will say that the equation is parabolic, elliptic or hyperbolic at the given point, not at the given region. For example, you have that partial differential equation. This is second order partial differential equation, famously known as Laplace equation. You have to compare that with original form. So just look, write down formally uxx plus uyy equal to 0. Okay. If you compare this, okay, compare with equation, which equation 2? Okay, I think we have named the general form as 2 or 1. Yes, 2. Okay. So if you compare with equation 2, what you will get? You will get that capital A was coefficient of uxx, this will be 1. Capital B was coefficient of uxy, this is 0 in our case, and capital C was coefficient of uyy, this is also 1. I am not focusing my attention towards D, E, F and G constants, because they are not necessary to accomplish or to verify the type or the classification of partial differential equation, this, because they you have to focus only on the principal part. So this is the principal part only. Okay, and there are 3 constants A, B, C which are used for the discriminant. So don't be rigorous or don't be very conscious regarding the other constants. So what will be the discriminant? This implies that the discriminant will be what? Discriminant will be equal to, okay, you just name that discriminant, and that will be equal to b square, okay, formally b square minus 4ac. But b and ac are not functions of xy, they are only constants in our case. Sometimes they can be constant, but sometimes they are not. So what is the quantity? B has value 0, C is identically 1 and A is identical 1. They are constants with respect to x and y. So what will be the answer? Answer will be minus 4, which is always negative for all. You have to write for all. Which points this is negative? For which point this is negative? You will say that for all x, y belongs to what? You have no condition. You will say belongs to R square. So for all x, y belonging to R square, there your discriminant will be negative, because it does not depend upon x, y. So your domain of interest will be R square, because on the whole plane your equation is behaving like a elliptic form of partial differential equation. So your partial differential equation is what? Your partial differential equation is elliptic type for all x, y. You don't have to bother for x, y. Similarly, if you focus on heat equation, so you can easily solve by yourself. Here A is minus 1 comparing with the equation 2, B is 0, C is 0. So your discriminant is 0, and you will easily say that your equation is parabolic for all x, y. And again, if you compare for that case, this will be hyperbolic, and this is the problem where x happens. Okay, look, there is variable coefficient C. So B is 0 again, A is 1. If you calculate the discriminant, this will be minus 4x. So if x is negative, the answer will be positive all the time. Okay, for x negative, the quantity minus 4x will be positive, and the equation will be hyperbolic for that case. And if x is positive, the quantity minus 4x will be negative, and the equation will be elliptic for that case. So this example shows that equations with variable coefficients can change their behavior in different regions of the domain. So this was I was trying to tell you before. For the classification regarding any regarding linear second order partial differential equation, but with respect to n independent variable is not part for your course. So I am just neglecting or not focusing on this, because this is not your part of study for n independent variables. So there are again examples for related to this part, but you are not supposed to do that. Okay, there are examples regarding classification. You have to classify that which partial differential equation is elliptic, parabolic or hyperbolic. Only focus your attention towards principal part, but this equation is not of your interest, because this has independent variables 3, I think. Yes, u depends upon x, y, z. So for independent variables more than 2 is not part of your syllabus, so you will not do question 2 and 3. You just focus your attention towards question 1. So this is the practice problem that you have to understand and develop the understanding regarding classification of second order partial differential equations which are linear. So this was today's lecture, that you should have the understanding regarding second order partial differential equation firstly, and then you should understand that it is not so easy to study the methods regarding any second order partial differential equation, whether it is linear or non-linear. We are mainly focused towards linear second order partial differential equations, and we will try to solve this equation with variable coefficients. And this is the standard form for linear second order partial differential equation with variable coefficients. We have studied today, I am revising what are the constants, and analogously this equation is something replica of the second order polynomial equation in basic algebra, which was given in the literature, given in the lecture slides as well. Ax square plus bxy plus cy square. Yes, this equation 3. And we have developed a classification criteria depending upon the equation 3, that our partial differential equation which is linear depends upon one famous or classical parameter, which is discriminant, and on dependent upon the signs of the discriminant we will tell that which partial differential equation is parabolic, elliptic or hyperbolic at which domain. Okay, you have to specify as well the variables x and y. Thank you very much, and try to solve these problems which are related, just to observe and analyze in which region the given equations will be parabolic, elliptic or hyperbolic. In the next lecture we will try to start and study the problems related to linear second order partial differential equations, and we will try to develop some methodology in order to solve them. Thank you very much for listening.